And that's like combined with the Gauss theorem tells you how to eat pizza. So that's one application. This observation, you can push that like way further and like say like, okay, now we know that something gets like a lot of stability here just by curvature, like putting some curvature in something in one direction gives you stability in something that is like in the opposite directions, right? So like I put in curvature in one direction, so this one is easy to do, right? Like it's just like taking this sheet of paper and just putting a bit of curvature in there. And then what I get is like stability in the opposite direction. So like here's the curvature direction, and then I get like stability in this like opposite direction. And that's, for example, what can be used in these card boxes. If you get like a paper from Taobao, a package, then like it's very thin material actually, but it's very stable. You can put like these boxes on top of each other and move, and that's like still works. And that actually comes back to having like the inner structure, which is just like some small bendings, and then what you get is like it's very hard to now bend it over in the opposite directions. So it's very hard to like put now something in this direction of curvature just by putting some like very simple curvature in there. And here we have an example from architecture. That's a nice place in Valencia in Spain. It's a museum. And you can see it's like the same principle. It's just like the pizza on its head, so to speak. So what you have here is a pizza. You bend that over, and then you get this kind of shape. And what you have is now that it's like instead of like the gravitation is pulling this one, it's like now we have the stability that this one is like the gravity is like pulling downwards, but it's very stable. It's not like you need a lot of force on the tip to actually bend it over. And that's why you can reach relatively far surfaces that stretch out very far, but just like bending or giving it some connection in some of the opposite directions. So that's like one of the really important applications of curvature and like the stability that you get like directly from the Gauss theorem, combined with this insight in physics that like isometry transformations are usually cheap to do. Non-isometric things are like very expensive or cost a lot of energy or force. So that gives you some nice applications in the direct world for like something important like as the Gauss theorem. Okay, so that's like some applications of the Gauss theorem. I would like to discuss some more applications for today in mathematics, where we can like, I think that's like not for me. It's like quantum field theory, also very interesting. So I would like to discuss some applications of the Gauss curvature to rigidity in some ways of surfaces. And I want to give you some taste of that. And the idea here is that maybe like going back to the analog to the curves is like a good idea. So in the curve example, what we saw is that once we give you like the two functions, namely the function of the curvature and the function of the twist, the kappa and the tau, once I give you these two functions, you can always reconstruct the curve from that. So that was like this reconstruction theorem from curves that tell you essentially curvature and twisting gives you the curve back. So you can now think about like a net logical question would be, what is the analog of that construction for surfaces? Where we say, okay, we give ourselves, say, the Gauss curvature, can we reconstruct the surface? So I give you some complicated function, can you construct the surface back from that? And usually the answer is no. Usually you need more information than the curvature. But sometimes if you put a little bit more information in there or like have some particular settings, you can actually say quite a bit. And that's like an example. reconstruction of surfaces from curvature. So spoiler is the answer in general, no. So in general, it's too much to hope that you really can reconstruct the whole surface by just giving you, if I give you the Gauss curvature. But sometimes, under a bit more information, sometimes it works. So for example, we have the following result. If we have S some surface such that every 2 points on S can be connected by a path in S. So what we don't want is like something that we have here an environment and here an environment, and then we have like a point here and a point here, and we can't connect them by some path. So we don't want like setting like that, but every point, like we have a nice surface where we reach like every point when we start from one point. And we also assume, and every point is an umbilic point. So that's a very special situation, right? I told you last time that umbilic points are usually isolated points in a sea of elliptic points. But here we assume that every point of the surface is umbilic. So that's a very strong assumption. But then we can get like some nice results, namely then S as constant Gaussian curvature which is greater than 0, and there are two different cases. The first one is if k happens to be 0, then S is part of the plane. And if k is greater than 0, then S is part of the sphere. Of radius 1 over the square root of k. So that's a theorem that tells you that that under this really strong additional assumption, which is really important that we make that, there's only two different cases. Namely, either we are like have some part of the plane where we just have like something planar, and then we cut out like some nice surface in there, or we say if k is equal to 0, bigger than 0, then it's part of the sphere. So these are the only two cases if every point is an oblique point. So let's have a look how to prove that. So the starting point is that we have E1, E2, and E3, and frame adapted adapted to S. Since every point is symbolic, what we get here is that the shape operator applied to E1 is kappa times E1, and the shape operator applied to E2 is kappa of E2 for some function kappa. So usually we have like some eigenvalues, but since every point is umbilic, we can ensure that these functions are the same. Thus, E1, E2, and E3 is what we call the Darboux theorem. So from last time, once we were talking about these Darboux theorems, we know we have like the following equation for these kappa functions that we can apply it to E1 and get 0, and we can also apply it to kappa to E2 and get 0. So that was like from last time we had some equations that involved here, like that were telling you what is d kappa, and it was given as like kappa 1 minus kappa 2, or with some signs in there. But now kappa 1 and kappa 2 are the same, because by assumption every point was umbilic. So that means that d kappa 1 and d kappa 2 applied to E1 and E2 are 0. From this one, we directly see that d kappa 1 has to be 0, because we evaluated on a basis, and regardless of the basis vector, we always get 0. So d of something is 0 if and only if the function is constant. So we have the kappa is the constant, and then clearly k, which is just k. Okay, now it's the capital K is the small k. So like, I'm sorry, like that's a kappa here. So the kappa squared, the principal curvature squared, since they are like the same, gives us the Gaussian curvature. The Gaussian curvature is given as the square. It's clearly something positive or non-negative at least, because it's the square, and because k is constant, the Gauss curvature itself is also constant. So that's the first part, where we say like that S had to be a Gaussian curvature, which is bigger than 0. So now we analyzed the two cases. I will do the first case, and the second case will be your homework, where we say, okay, now what happens if you have constant Gaussian curvature, which is 0? How do we show that we are in the plane? So the first, assume k equals to 0. So the idea would be to show that it's a plane, or like some part of the plane. So what this means is that we have the normal vector would be constant. So what we have to show, well, I mean that's like one part, because k equals to 0 implies that this formula that the kappa has to be 0, So that in particular means that S has to be 0. The shape operator has to be 0. And that means, because the shape operator was measuring the change of the normal, means that the normal of P is constant, say like some vector n0. So the idea is now show that S is contained in plane that is orthogonal to n0. So that would be the guess, right? You have like a constant normal vector, and then the guess would be the surface that we're looking at is like the plane that is orthogonal to the normal vector. So for this, let C, let's say from 0 to 1, be an arbitrary curve. And consider like the help function, which is defined by f of t equals to the difference between c of t and c0 of t, and then taking the inner product with n0. So we have that's our C. And then we measure at every point. Let's say we are here. Then this vector here, the C of t minus ct, is this vector ct minus c0. It's the vector that points to ct, C of t starting from C of 0. And we would like to show that this expression is always 0. So let's calculate f of the derivative of that at some arbitrary point. What this is just C of t applied to n0. But this one is has to vanish because this one is tangent to S, and we take the inner product with the normal vector. So that gives us nice 0. So it's f of t is a constant function, and also we have f of 0, which if you plug in t equals to 0, we get c of 0 minus c of 0, so that's 0. So we have a constant function, or like a function with derivatives 0, which starts at 0, which means that f of t has to be constant, equal to 0, and that implies that c of t minus c of 0 is orthogonal to n of 0 for all t. So that means, because these one can be arbitrary points, so for all p and q in our surface, we can find a curve that goes like, maybe I'll write it like this. What we get now is that for an arbitrary points, we can just choose a curve that connects these points. So that means that p minus q is orthogonal to n0. And that's clearly only the case of if S is a part of plane. And the result, the second result, that if k is bigger than 0, then S is part of the sphere, can be proven in a very similar way. We just have to choose a slightly different function instead of like looking something at the plane. You maybe have something that is related to the radius. Okay. So that's one way, like a relatively simple way how to construct, or say like at least once you know the curvature information, you know what kind of surface you have. Right? So that's like the idea of these kind of like theorems, and also of the next theorem is like I only give you curvature information, only say like the Gauss curvature has a certain property, and then you say, hey, that's part of the plane, that's something part of the sphere. So that's the nice part. And the next theorem is like very similar in that spirit. If S is a compact surface in R3 with constant Gaussian curvature, which is bigger than 0, then S is the sphere of radius. So that's a theorem which is like very similar in spirit, but like here we assumed that every point is already an oblique point from the start. This theorem is a little bit different taste. In this case, we replace this assumption by something that is a bit more, like in some way, like a bit weaker, namely saying that it's only a compact surface with constant Gauss curvature. And then we also get that its automatic has to be the sphere. And here, I don't want to go in a proof, but one remark is compactness is important. For example, like if you look at the football, like the American football, which is like, it's not like a sphere, but it's like, it has like this kind of shape where it's a bit like like stretch in a longitude. So that's the football. This one also has constant Gauss curvature. But we have to remove like these points here because there it's not smooth. And without these points, it's not compact. These points, it's not smooth. But if you remove these 2 points, then what you end up is essentially as the topology of a cylinder, and it's like it goes on for infinite. So it's like not compact, and then that means that it's an example of a non-compact surface which has constant Gauss curvature, and clearly this one is not part of the sphere of radius 1 over square root of kappa. Okay, so that gives you hopefully some idea of like this idea, the construction that once you know some Gauss curvature conditions, especially if you have like a constant Gauss curvature, that gives you quite a lot of information about the surface, and it's very restrictive. And like you can push this kind of like ideas very far and say like if you know some kind of information about the Gauss curvature, you usually have like very strict properties about the surface in itself. And there are many different theorems that push that in different ways and like say like how much can you have curvature in one region and then can you shuffle them around, for example. So that's like, many different results about Gaussian curvature or like surfaces with some control of the Gaussian curvature. And these two theorems give you some idea of like how they may look like. So now I would like to, in some way, stop a little bit this discussion of like the curvature of surfaces and come back to like a different viewpoint, which will also be, of course, connected to the geometry and of the curvature of a surface. And that's it's like by looking at curves in the surface. So far what we did was usually we used frames to study the curvature, but you can also say like we discussed already a little bit that the normal curvature was related to something that you measure with the curves in the surface. So we would like to maybe push that a little bit further and study a bit more how to connect the curvature of the surface to behavior of the curves in the surface. That will be a part of the next few hours. And that's what is especially one part of curves that we look at are called geodesics. And geodesics are like certain kind of curves that you can think of like the generalization of a straight line in a plane. So like if you look at the plane, like the most simplest curve that you can think of are just like lines that go like in a certain direction and keep going forever. So in the plane, the following are equivalent. Equivalent for a curve. So we have a planar curve. The first thing is that C is a straight line. So what other properties do you know are equivalent of the curve being a straight line? How do you, like if I give you a curve, how do you say the curve is a straight line? So we need 3 more properties that are equivalent to the curve being a straight line. Its variance. What do you mean? The variation of what? variation, you mean C dot equals 0? That would be a variation of the curve, right? What is the, like, I'm now tempted to write this as the total, but sorry. But like, what do you mean with like variation? Fermat, okay.
The light travel through the shortest path.
Yes.
So I mean the variation.
Okay, so you mean yes, it's an extrema, or like the variation of the extrema of the length function. So if you look at, like, you measure the length, then the straight line is the one that has like a certain extreme thing, which is nothing else in this simple case to say it's equivalent to the straight line is the shortest path between 2 points. So if you have two different points, and you look at like all different paths that connect A to B, then the straight path is the shortest distance between two of these paths. So that's like equivalent to C being a straight path. So whatever properties do you know? Like maybe like more simple ones. I think you said like already one that was good. And kappa is the curvature of the curve. Yes. So that's here is 0. And in this particular case, it's like equivalent to actually that the acceleration is 0, because that's essentially the curvature of the curve. One property about the tangent vectors. What is so special about the straight line and the tangent vectors? Yes. So they are constant, or like a different way to say is that C of t are parallel. So these are like the properties that we have for a curve in the plane. So that's like very particular to having a curve in the plane. And now you can say, okay, what are the equivalent of these properties if I have a curve that is like actually following something on the surface? So, for example, if you now take, let's say, the cylinder, you have the cylinder, and we could like ask, for example, what is the shortest path between this point here and this point here? What is the shortest path? Is there like something, like how do you connect these in a certain way so that like the distance between these points is like the shortest, that you travel the shortest amount of time? You can also say, for example, it looks like that like there are special types of curves which are going just up, which would be just like something that is not like curved. But clearly you can't connect 2 points, for example, always by like a straight line in this sense. And some curves, some curvature surfaces don't even have like straight lines, but would be a straight line on an object like that. Like you can go around, but in which sense is that a straight line? So that's like the topic for for next time. I think it's a good moment to stop before I write like formulas and stuff. But so that's like the point for next time. We will study curves and we generalize these different properties that we have. Namely that it's a straight line, and we say we give that a name, and then we try to find like some properties about the curvature that would be equivalent to that being a straight line. Some kind of properties about the tangent vectors, and then we discuss about like the length function and saying like that it's the shortest path in a certain way. So that will be the subject for next time. So I think I just close today 5 minutes earlier, so you can enjoy your evening a bit earlier. Maybe as compensation for that, like last time it took a little bit longer with the homeworks. So yeah, that was it for today, and then enjoy your pizza.
What is the context service? We talked about that a little bit like 2 lectures ago. It means that what's the definition? Like it's essentially saying that you have like rectangular like objects, and you can like find it remaining to cover your whole surface. And that was really like the important idea of finite remaining. So like the cylinder, for example, goes on like to infinite, so you can't have like finite remaining rectangles. And that's with this object there. It's like if you remove these endpoints, then you need like infinite remaining because they could go on essentially forever.
I just have pieces before the lecture.
Okay. parallel. This vector you this vector and you transport it to this lower point, just like intersection parallel. So that's a really good question. What is, for example, like a slope movement of like a carrier on a surface that you see? What is like how you would see like when a vector carrier on the sphere. So that's going to be exactly a with this part. So that's really good stuff. Okay. And enjoy your evening.